Our next rule, and I think if we're keeping count, we're at rule 8, is called the chain rule. Chain rule, we're going to spend today looking at chain rule in a very algebraic sense, and we're going to spend the next lesson focusing more on a generic and a trig-based chain rule focus. So, what a chain rule is. First of all, let's talk about why we need a chain rule. So if we think about functions that are singular functions, basic functions, everything in this first column what I would consider your very simple basic function. Your first one, y equals x squared plus 1, it's just a polynomial. Second one is just a singular trig function, just sine of x. Third one is 3x plus 2, basic polynomials trig. Well, here's what we can't do yet with our rules that we have. What happens if we take that same function and we do another operation to it? So for example, if you look at this first one, I still have the x squared plus 1, but I also square rooted it. So I have this outer function that's being introduced. Same thing with the second one. Instead of having just a sine of x, what if it's a sine of 5x? What if I change the angle? Or what if the sine is being squared? So again, introducing another operation or another function. And then the last one, instead of just a 3x plus 2, what if it's to 3x plus 2 to a power of 6 or to a power of 3 or to a power of 1/2? The idea is I need the chain rule to take the derivative of what is called composite functions. Composite functions is basically like a function inside a function. It's a function that has multiple layers is another way to think of it. So when we work with these composite functions, the first thing I want to make sure you're comfortable with from an algebra standpoint is that you understand like the inner and outer function or what are the multiple parts. So often, for some reason, they use the letter U to be that inner piece, or sometimes they call it the g of x. You might remember from Algebra 1, the way we often write a composite function is we write it as f of g of x. So this idea that you have this inner function and then something's being done to it. In calculus, sometimes we call that inner function the u function, which makes things interesting because then it looks like I'm basically just saying fu. So when we look at some of these ones at the bottom, when we talk about the inner piece and what's being done to it, when you look at the first one, the square root of x squared plus 1, that inner function is the x squared plus 1 piece. We call that the u, or the innermost function. And then what's being done to it is it's being square rooted, or it's being taken to the 1/2 power. So we have those like layers that we're deciphering. For our trig one, if it was, for example, sine of 5x, that inner function would be the actual angle 5x. And what's being done to it, or and this sounds kind of strange, is it's being signed. It's the angle of sine. So we would say it's a sine of u. And then for the third one, the 3x plus 2 one would be your inner function. And what's being done to it is it's being taken to the 6th power. So first, just kind of an algebra conversation of how do we identify these composite functions. Now here's how we actually derive it. So here's our chain rule. And again, it is used anytime we're trying to derive these composite or these like layered functions. The notation is something you definitely want to jot down, and then I will explain it. If you need to pause the video to jot it down, you can do that. It's not quite as, I don't know the best way to explain it, like intrinsic as the product rule and quotient rule, where I feel like those ones kind of naturally like write what you do. This one might look a little strange. Essentially, what the notation is saying is you're going to take the derivative of that outer function, which is often going to be a power rule, and you're going to keep the inside the same. So that's what this piece is. You're going to derive the outer piece using whatever derivative rule is needed. And then when you're done, you have to keep taking away those layers and you have to derive the inside layer. So that's the derivative of what's inside. So it's doing kind of like the outer derivative, which is often a power rule, especially today, you're going to see a lot of power rules. And then remembering to derive by what's inside, kind of peeling back the layers and making sure we're taking the derivative of each piece. Sometimes I've seen it written like this, where they write it as a dy du times du dx, and du dx is just the derivative of what's inside. I actually think for an AP standpoint, this notation is probably what you're going to see the absolute most. So let me show you how it works in terms of just algebra-based problems, and we'll really save the trig ones for later. So when you have an algebra-based function, which is going to be a function to a power, a function in the numerator, the denominator, a function under a radical, the way that we derive it is you're going to do the outer derivative first. So what I mean by that is you're going to bring the power out front because it's a power rule. You're going to take this to a power 1 less, which is what you do with a power rule, power front, power 1 less. But then what you need to remember is you also need to derive by the, or multiply by the derivative of whatever was that inner function. So the derivative of 3x plus 2 is 3. Now, the only simplifying I usually do is if I have coefficients I can multiply together, I do that. You're not going to see much additional simplifying with these at all. Nobody's going to make you take that to the fifth power and multiply that all out. So again, you're deriving the outer piece by doing a power rule, power out front, power one less, and then remembering the derivative of what's inside. If it's being taken to with a radical, you want to rewrite it with exponents. So again, radical notation is of no help to us. So our power comes out front. We take this function to a power one less. And then again, we multiply by the derivative of the inner function. So the derivative of the inner function is 2x. A little cleanup on this one is necessary. You don't want to leave negative exponents, and you may also notice that the 1/2 and the 2 cancel. So your answer is x over x squared plus 1 to the half, or you can write it under a radical. You can go back to radical notation. Show you a few more. So the next one's a pretty quick one. Anytime you have whole number powers, really basic algebra, those are going to be the simplest. So power comes out front. You're going to take this to a power one less. And then you're going to multiply by the derivative of what's inside. The derivative of 4x squared plus 2 is 8x. I'm not sure if Delta Math asks for a lot of simplifying, it will tell you, but the one thing that you can often do is multiply those single terms together, but you're not going to be able to do anything with what's in parentheses. If you have your function in the bottom, you want to rewrite it with a negative exponent. This is going to help avoid more quotient rules. I feel like there's a lot of rules that we have to avoid the quotient rule because it tends to be one of the longest ones we use. So by rewriting it, my power comes out front. I'm going to take it to a power one less, which is now going to be -2. And then the derivative of what's inside. In this case, the derivative of what's inside is 1. I don't want to leave negative exponents in my answer, so my answer is going to be written as -1 over x plus 1 squared. Doesn't want to write that. There you go. For the next one, you need to be comfortable with your fractional exponents and radical notation from Algebra 2. This is the same as x squared plus 4 being taken to the 4/3 power. Again, it's power over root. So your power comes out front. You drop it to a power one less. And then you multiply by the derivative of what's inside. Again, cleanup is very limited. You could multiply the 4 and the 2x together and write it as 8x over 3, and then you still have the x squared plus 4 to the third, but not much simplifying. And then finally, the last one. Again, power comes out front. Take it to a power one less. And then multiply by the derivative of what's inside. Derivative of what's inside is 3 minus 4x. And you can leave it just in that factored form in those parentheses. So it is no problem to just type in all of that. You don't have to distribute that 3 to that second 4x piece. So that is your chain rule specific to algebra-based questions. We're going to get more into some that have multi-level here in a second. We're going to get into ones that are generic and trig in our next class, but it gives you definitely a concrete foundation of what this chain rule is and how we use it.